This is problem 6, and this problem will be helpful to you when you look at your homework problems, which are Fundamental Problem 5 and Problem 20. This is our last example problem from section 12.2, and as we solve this problem, we're going to talk a little bit about graphs, which is going to prepare us for what we see in section 12.3. So, for problem 12.6, we have the position of a particle along a straight line is given by s is equal to 1.5 times t cubed minus 13.5 times t squared plus 22.5 times t in feet, where t is in seconds. We want to determine the position of the particle when t is equal to 6 seconds and the total distance it travels during the 6-second time interval. And we're given a hint to plot the path to determine the total distance traveled. Okay, we're looking for the total distance, which is different than the displacement, or at least it's possible for it to be different than the displacement. So before we actually start solving this problem, let's look at some different situations that we could have for position versus time graphs. So the easiest situation would be if the object is not moving at all. So let's say I put the object 2 feet away from the origin in the positive direction, and it just sits there, not moving. Then you would have a flat graph for position versus time. The distance that the object travels during any time interval between here and here, where I've drawn the graph, would be 0 since it's not going anywhere, and the displacement is also 0. So nothing really interesting is going on there. You could have a linear and not flat position versus time graph, and let's just say something like this. And so we have a position which is becoming more and more positive as time goes on. You could pick 2 points, so let's just say here we have T1, here we have T2, and you could find the position, we'll call that S1 at T1, and the position S2 at T2, and then the displacement is S2 minus S1, which is the same as the total distance traveled. It gets more interesting if you have something quadratic for your position versus time graph. So that could be something like this. This would be the graph that you would have, the type of graph that you would have if you throw something up in the air, and then here we have a turning point where the velocity is equal to 0, and then the object starts going back down again. This should be review for you from Physics 161. And you could pick 2 points again. So let's say T1 is here and T2 is here, and I can calculate the position at T1 and the position at T2. In this situation, let's say that S1 and S2 are equal to each other. If you look at the displacement between time 1 and time 2, you would get 0. However, the total distance traveled between time 1 and time 2 is not 0. However, if I pick a different point, let's say I look at the total distance traveled between this point here and this point here, that would be the same as the displacement. It would only be if I pick a point after the turning point for my final position that the distance and the displacement would be different. So this is when the position is not changing at all. This would be when the position is a linear function of time. This is when the position is a quadratic function of time. And if your equation is something like what we have in this problem here, where you have a t cubed, then you may also need to take into consideration the turning points that you have in order to find the total distance traveled. So we're going to look at how to do that when we solve problem 6. But before we move on, let's do a little bit more review from Physics 161. And I have position versus time graphs here. If I want to draw the velocity versus time graphs from the position versus time graphs, what is it that I need to look at? So I have position versus time, and I want to draw velocity versus time. So I can take the derivative of the position versus time graph. This is a flat line. If you take the derivative, you just get 0. Here we have something linear. If I take the derivative, the slope is positive, so I get something positive. So we'll just say something like that. Here I have a quadratic function. If I take the derivative at this point here, I get 0. So the velocity at that point is 0. Here, the slope is positive. Here, the slope is negative. So I get something like this for velocity versus time. We don't have any turning points in this graph here, and the velocity is 0 the whole time because the object isn't moving. We don't have any turning points here either. The object is always moving in the positive direction, and our velocity is always positive. Here we have a turning point, and when the object turns around, the velocity is 0, so the slope of the position versus time graph is 0, and the velocity is 0 when the object turns around. This should make sense to you because if the object is turning around, it has to stop going. If it's going in the positive direction initially, it has to stop going in the positive direction and start going in the negative direction, so it has to cross 0. And also, if you remember from Calc 1, if you want to find the maximum position for this graph, at the maximum position, the slope has to be equal to 0, and that's where we get the velocity being equal to 0 for our graph here. So, one thing that I want to mention before moving on to problem 6. You are going to do fundamental problem 5 for homework. In fundamental problem 5, you're given the position of the particle. This is a quadratic function, which means you are going to have a turning point, at least if you look at a large enough interval of time. You have to determine the time when the velocity of the particle is 0. That's the turning point, and the total distance traveled when the particle, or the total distance traveled by the particle when t is equal to 3 seconds. Assuming that we're starting at 0 seconds and going to 3 seconds. If the velocity of the particle is 0 between 0 and 3 seconds, then you have to take that into consideration when you find the total distance traveled. If that turning point is after 3 seconds, that's like what we looked at here. If this is your initial point and your final point is before the turning point, the displacement and the distance are the same. But if your final point is after the turning point, the displacement and the distance are not the same, so you have to do what we're going to do in problem 6 in order to find the total distance traveled. For problem 20, which is also going to be a homework problem, the velocity of the particle is given. The velocity is a quadratic function of time. We didn't look at that here. Here we had velocity as a linear function of time. But if the velocity is a quadratic function of time, then you are definitely going to have turning points when you look at the position versus time graph. So again, when you look for the total distance traveled, you have to know when the velocity is 0 in order to be able to determine what the total distance traveled is. Okay, so that's coming up for homework, and now we're going to look at problem 6. Okay, so we have, not fundamental problem 6, this problem 6. Okay, so the position of the particle is given, so S is equal to 1.5 t cubed minus 13.5 t squared plus 22.5 times t in units of feet. We want to determine the position of the particle when t is equal to 6 seconds. That is easy. We just plug in 6. And the total distance traveled. Okay, so first of all, let's just plug in 6 and get that part out of the way. So we have 1.5 times 6 cubed minus 13.5 times 6 squared plus 22.5 times 6. And for that, you should get negative 27 feet. If you plug in time in seconds, the position is in feet. Okay, so now we can focus on finding the total distance traveled. So we need to first find the turning points. And as we just discussed, those turning points are where the velocity is equal to 0. At a turning point, the position is either going to be a local max or a local min, and in either case, the derivative at that point is equal to 0, which means the velocity is equal to 0. So I'm going to take the derivative of the position with respect to time. So I have 1.5 times t cubed. The derivative of that is 3 times 1.5, which is 4.5 times t squared. Then I have minus 13.5 times t squared. Taking the derivative of that gives me negative 27 times t. And then when I take the derivative of 22.5 times t, I get 22.5. Now I want to find when the velocity is equal to 0. So I take this and I set it equal to 0. And then we're going to solve. You can solve it on your own. And when you do, you should get, for the solutions, which you can get using the quadratic equation, we have t is equal to 3 plus or minus 2, which means either 1 second or 5 seconds. So if you graph this, if you graph the position versus time, you're going to start off at 0, because when you plug 0 in for time here, the position is 0. And then the position becomes positive. At 1 second, the slope is 0. So we have to have a slope of 0 here. We turn around, we're going to cross somewhere, and then at 5 seconds, again, we have a slope of 0. So at 5 seconds, we have a slope of 0. So the graph has to look something like that. So we found the time for the two different turning points, and we are looking at the total distance traveled at 6 seconds. So we have two turning points between 0 and 6 seconds. This is a position versus time graph. If the object is moving in one dimension, we could draw or trace out the path that the object takes. So we're starting off at the origin, and then the object is moving, let's say the positive direction is to the right, so the object is going to the right, and then it turns around and goes back this way again. Now if it's going in one dimension, it's going back on the same path that it went out on, but we're going to drop down a little bit just so we're not drawing everything right on top of itself. Okay, and then we go over this way, and then we turn around at 5 seconds, and then we start going back, but we don't make it all the way back to 0. Okay, so if I just took the position of the particle at 0 and the position of the particle at 6 seconds and did the difference of those two, that would give me the displacement. That would be the distance from here to here. But that's not what I want. I want the total distance traveled. So I'm going to do this in 3 different segments. I'm going to find this distance, and this distance, and this distance here, and that will give me the total distance traveled. So I'm going to go from 0 to the first turning point, then from the first turning point to the second turning point, and then from the second turning point to the final time. That gives me the total distance traveled. I have my equation for the position, and I have the time for the different turning points, so I can just take that and plug that all in to find the position at each of those times, and then from that I can find all the distances that I need. So I'm going to need the position when time is equal to 0. I need the position at the first turning point, which is 1 second. I need the position at the second turning point, which is at 5 seconds. And I need the position at the final time, which is 6 seconds. Okay, we already said the position when time is equal to 0 is 0. For this, I'm not going to write it all out, but just take 1, plug it into the equation here, and you should get 10.5 feet. And then take 5 seconds, plug it in here, and you should get negative 37.5 feet. It makes sense that you get something negative because this position here is the position at the first turning point, so that should be positive. Over here we're to the left of the origin, so that should be negative. This is 37.5. And then finally, oh, we already found this. This is negative 27 feet. Okay, and then to finish the problem, there's not really an equation that we're given for this, but you can kind of just do it from looking at the picture that we drew. So I need this distance plus this distance plus this distance. Okay, there's probably an easier way to do it, but in general, you can find the total distance by looking at the first segment, and since it's the distance, we would do the absolute value of 10.5 minus 0, so first turning point minus initial position, plus then going from the first turning point to the second turning point, that'd be negative 37.5 minus 10.5, or again, if you just look at the picture, you can see you need to add 10.5 and 37.5 to get this distance here. And then finally, we need this little segment here. So that would be final position of negative 27 minus the position for this turning point, which is negative, so that's going to be plus 37.5. This is, of course, 10.5. This is from here to here, 10.5 plus 37.5, that's 48. And then this would be this little bit here, which is 10.5. Okay, I did it this way because if you have to solve more complicated problems, you can always do it like this. But just from looking at the picture that we drew here, I would say 10.5, from here to here is another 10.5, so it would be 10.5 plus 10.5 plus this bit here, which is 37.5, and then just add the difference between those two. And you could get the final answer that way also. So I really don't care how you do it from this point on, but you should get 69 feet for the total distance traveled. And that concludes problem 6. And that also concludes section 12.2.